Hello, we are group number 11. I'm Emily and my group members are Grace and Mahan. We will be talking about our design and analysis of a non-overlapping iris diaphragm. The goal of our project was to create a micro-scale iris diaphragm to be used as a way to control the aperture of a smartphone camera. One of the major benefits of having control over the aperture size is the ability to use optical zoom opposed to the standard digital zoom currently used in most smartphones, as optical zoom provides higher image quality. In addition, having control over the aperture size allows the user to have control over the brightness of an image as well as the depth of field. Originally, we were going to test 3 different actuation methods: manual actuation, thermal actuation by using hot-cooled arms, and thermal actuation using chevron actuators. Each design was developed with a method to close the initial gaps set between the leaves and then deflect further, making the aperture in the center smaller. Due to testing limitations, the hot-cooled arm design did not move forward into fabrication. The manual design has a central ring that is anchored to the substrate with 4 springs. There is a small tab sticking out of the ring which can be moved by a probe tip to instill rotation of the ring. The ring is prevented from moving too far by a small circular anchor positioned opposite of the tab. The 6 sleeves are connected to the ring by thin beams which bend around the comma-shaped anchors as the ring is twisted, forcing the aperture to close as the ring spins. We made 2 different mechanical designs, one with springs perpendicular to the ring and one with springs tangent to the ring to compare them. To analyze our selected mechanical designs, during testing we tallied the number of catastrophic failures, parametric failures, and successes of each version with the intent to move forward with the version that had the highest degree of success. In addition, we took note of the degree of rotation of the rings to determine if the springs were of appropriate size. As will be discussed later, this did not yield any useful information as both versions performed exactly the same during testing.
For our thermal actuation design, we had 6 leaves. Each of them was connected to a chevron actuator, and each chevron actuator was anchored to the substrate using 2 anchors. The setup was designed in such a way that the combination of movements produced by the chevron actuator, the thermal expansions, and torsions of the arms make the central gap smaller. 2 sets of designs were fabricated. First, the chevron actuator with 5-degree initial angle, and second, the chevron actuator with 10-degree initial angle. To stimulate all 6 actuators at the same time, we have planned to use hot plates. So in order to analyze our thermal design, we used 2 different tools. First, by programming in the MATLAB, we studied the effect of different design parameters on the performance of the chevron actuator, and we achieved the best design parameter values. And then by using those values in a FEM software, we simulate the whole setup, and it was observed that the performance of the setup is satisfactory. So this is our initial layout. It consisted of 2 types of thermal actuators, testing both 5-degree and 10-degree chevron angles, and 2 types of mechanical actuators to test the perpendicular versus the tangent spring placement.
Unfortunately, despite following the basic design rules, none of our initial layouts of either design were viable, and therefore all testing failed. As can be seen in the photos of the chips, the leaves and anchors did not fabricate properly and fuse together. When the chevron was tested, the heat was increased by 200 degrees from room temperature, and there was no apparent change in the angle of the chevron or in the center of the iris. Testing the manual actuator revealed a couple of problems. The tab to push on the spring was too small to be easily caught by the probe tip, the springs were stuck together, and the leaves and anchors were fused. Although the anchors were 50 microns, a lot of them lifted before testing or shortly into testing. As we placed the minimum spacing between most of the close components to save space on the final design, this caused catastrophic failure throughout all the versions. Unless it is not necessary that your parts are completely isolated from each other, a tolerance to the minimum spacing value should be added. Even though the control tab seemed to be a fairly reasonable size on the layout diagram, it was still incredibly small in real life and was very difficult to maneuver. The pictures seen here are our final designs as was submitted. The manual actuation was scaled up and the springs rotated. The thermal actuation design was modified to address the observed issues from experimental tests. For the mechanical design, we scaled the entire design by a factor of 2 to increase the minimum spacing between all components from 10 to 20 microns to avoid any errors yielded from fabrication. In addition to this, the springs were increased by another 1.5 times to decrease isolating points of stress and ensure the springs could move freely. The control tab was made larger to be able to move the ring more easily, and the springs were rotated by 22 degrees from the tangential direction to better align them with the direction of motion. The mechanical layout was analyzed using SOLIDWORKS to look at the stress concentrations on the different spring types. It was assumed the probe tip in the lab would exert a force of 0.1 millinewtons on the tab. In the SOLIDWORKS analysis, the force only operates in a straight path, and therefore the displacement and rotation are not what would be seen in successful fabrication. As can be seen in the pictures, the angled springs have the most stress on one spring nearest the tab, when the force is acting in the straight direction. The force concentration in the angled springs are better, though, than the perpendicular springs, which show high stress concentrations in multiple places when given the same amount of force.
As mentioned earlier, the design of thermal actuator was modified to fix the problems observed in the lab. The major modification is increasing the minimum spacing in the design from 10 microns to 17 microns. So in the new design, the initial gap at the center is more than the previous one. In order to be able to close this bigger initial central gap, we had to modify other parts of the design as well, such as decreasing the width of the chevron arms to 20 microns and setting the initial angle of chevron actuator to be 1 degree. But the first design parameter which we decided to change in order to improve the performance of the setup was the initial angle of the chevron actuator. To choose the proper angle, we benefited from the experiences we gained from labs, reviewing the literature, and conducting a parametric study. All results suggested that the less the initial angle, the more the displacement of the chevron actuator. As can be seen from the right side gives, by using the initial angle of 1 degree, we can close the central gap more in comparison with using initial angle of 5. As a result, we set the initial angle to be 1 degree. The second design parameter which was studied is the width of the chevron arm. After conducting a parametric study using FEM, it was observed that with 20 microns width arms, we can close the initial gap more in comparison with wider arms. It was also observed that by using 20 microns width arms, the maximum stress produced in the setup is still below the yield stress of SU8, which suggests a good safety factor. After modifying the design just out of curiosity, we wanted to see how much we can close the central gap if we had a more accurate fabrication process. As can be seen from the results, with the modified design, the central gap closure amount could be almost doubled if we had a better fabrication process. So, this is our final layout. It consists of only one type of thermal actuator, as it proved to be the most successful one during the simulation testing, and one type of mechanical actuator with the 22-degree angle springs. Additional mechanical actuators would have been tested as well to compare more spring sizes. However, due to the revamped minimum distance limitations, we only had enough space for 2.
Now, to discuss some potential questions you might have. First off, why are the tips of the leaves removed in the first thermal design? There's no real reason, except that I had the flu while we were modeling these, and in a feverish haze, I managed to convince myself that the tips would not fit the minimum size requirements. Why did we use the thicker SU8 layer for our chevron? Based on our analysis, if we used the thinner material as shown on the bottom GIF, the arms would deform out of plane and break before any effective contact was made. As for the thermal testing, we only used the hot plate because we only had access to 2 probes in the lab, allowing us only to test a single chevron at a time. But if this were to be implemented in real life, we could create circuitry to supply power to each chevron simultaneously. Finally, how much would this aperture allow a camera to zoom? If we consider the 10 micron gap version, because the diameter decreases from 35 to 10 microns, a zoom of 3.5 could be achieved. Thank you so much for listening.